in the spirit of the world collaboration, I'll talk about a story which is very much in progress. So very much welcome all corrections, comments. And also if I mess up the attributions of some of the prior results, please correct me, because I don't know the history of this so well. So it's based on its joint work with Ben Heuer and Vadim Vologodsky. So here's the question that we want to study. So let's say I'll just fix a P-adic, complete P-adic discretely valued field. So for example, QP. But I won't really mention this so often, but I'll rather work with complete algebraic closure. So all the story will be geometric, so I'll note it by C. So suppose I have some geometric object over this C, so maybe it's going to be a rigid-analytic variety. Over C, and I'll just assume from the outset that it's smooth. And maybe I'm interested in studying, say, sheaves on this. So let's say I'm interested in studying local systems on this variety. So maybe I have ZP local systems on it. Well, so far I could have chosen any coefficients, but it's been a theme that if you choose the coefficients which are also p-adic, then there are a lot of interesting maneuvers that you could do because your base field was also p-adic. So since now, the coefficient ring of your local systems embeds into the base field of your variety, here is one maneuver that you could do. So you could first form a C local system out of it. So maybe I should emphasize that this is pro-étale local systems, or which is the same as least sheaves in the étale sense. So I could go to C local systems. Again, I'm not going to say so much, talk so much about them, but I always assume that my C local systems admit an OC lattice. And then now the interesting maneuver, which uses that C is also is simultaneously the field of coefficients and the base field, is that I can further map it to what's called pro-étale vector bundles on X. Sure. Well, it's the same as maybe at this point it's okay if I just say it in the pro-étale topology. Yeah. Right. Where C is now a sheaf of rings in the pro-étale topology, which is associated to the topological field C. But I also assume that I have a lattice. And now, this maneuver, so I'll usually note it by L going to L tensor the pro-étale structure sheaf. So it's nice because, for instance, if X is proper, then this is fully faithful. So we did lose some information at this step, but we at least didn't lose any information at that step. And now the beautiful thing is that that target category now has a non-trivial reinterpretation. So let me leave the space on this board for later. Sure. Yeah. Right. Maybe that's better. But can I keep it this way? Yeah, is it okay? Yes. So it's the pro-étale site. So its value on every perfectoid ring is that perfectoid ring. Right. Yeah. So it's sort of it's crucial that here. Well, it's crucial here that we work in the analytic category, and pro-étale topology refers to that because otherwise, local systems with infinite monodromy wouldn't really give me. Most local systems otherwise wouldn't really give me a vector bundles. Right? They only become locally free after I complete my functions on my profinite covers. All right. So now, what is this reinterpretation? So it's this beautiful theorem under the name of P-adic Simpson correspondence. So in this form, it's due to Faltings, and then in this generality, that will be necessary for me, and the formalism as well, it's due to Heuer. So let me now assume right away that X is proper. X is smooth proper rigid space over C. And I'll have to outfit it with an additional structure. So let me assume that it comes equipped with a lift, which I'll call X tilde 2 to be consistent with my future notation. So this is a smooth adic space over beta plus modulo T squared, which I recall it's a certain natural square zero thickening of C, such that it's a lift of my X. And another piece of data that, so this is a choice that I'll make. And another choice that I'll make is I'd like a continuous group homomorphism, which I'll denote by exp. So it's a homomorphism from the additive group of my base field to a subgroup of the multiplicative group consisting of elements whose distance to 1 is strictly less than 1. And so this is a continuous homomorphism. Such that the composition of the logarithm and the exponential is the identity. Where what do I mean by logarithm? There is a map log going backwards given by the usual power series, because here I chose to work on the domain of convergence of this power series. And I'd like to make this choice of a splitting, which just has to be any abstract continuous homomorphism. There are many such choices. Then there is a linear algebraic description of this category of pro-étale vector bundles. So then pro-étale vector bundles on X. They're equivalent to what's called Higgs bundles. E on X. And let me recall that the Higgs bundle, it's a map. It's the data of a vector bundle plus the data of a map from E to E tensor 1 forms on my variety. And well, it's a kind of a nebulous correction, but let me emphasize that here, to be completely canonical, I'd like to think of this as 1 forms with 1 Tate twist. Again, mathematically, there's no difference, but I think it will be helpful for our orientation purposes as we go on. So it's an OX linear map such that it satisfies the usual flatness condition. Right? Right, maybe I should emphasize on the analytic side. Yes, thank you. Okay, so you have this equivalence. So notice that the categories that I'm identifying, they only depend on X, but the equivalence really depends on these two choices. All right, so now what I'd like to do is, so maybe if my original goal was studying ZP local systems, then maybe I'd like to somehow rectify the non-fully faithfulness of this functor. And I'm not going to do it completely, but I'd like to make one step towards that. So how could I do that? So one maneuver which I could do is I could also first notice that if I have a ZP local system, then in particular I get what's called a beta plus local system. So it's a continuous representation of the fundamental group of X with coefficients in a projective module over beta plus. And now I could do a similar maneuver, and I could go to the category which I'll call beta plus pro-étale, sorry, beta plus local systems. Well, sorry, the notation is all, so verbally they sound the same, but they are probably different categories, and I'm only going to be focusing on this one. So I'm going to rectify this in a second. So beta plus, it's a certain sheaf of rings on the pro-étale side of X. So let me maybe emphasize this. And I'm considering, so this is by definition, this is locally free sheaves, sheaves of modules over beta plus on X pro-étale. And I can make it maybe even somewhat more concrete. So it's a non-trivial theorem that this can be amounting to almost purity theorem, that this amounts to the following data, that for every affinoid perfectoid space, so for every the data of projective, finite projective 𝔹dR+ of R module, which I'll call MR, for every affinoid perfectoid space with ring of functions R mapping to my X. All right, so here I'm just saying it's, 𝔹dR+, it's this period sheaf, which on sort of X and its own tau covers, it has very few sections. It's, well, in a connected smooth variety, its sections are just the constants in 𝔹dR+. But on perfectoid spaces covering X, it has many more sections. And so I claim, so I'm looking at locally free sheaves of modules over that ring. And then it's a consequence of almost purity theorem that actually already on every perfectoid, affinoid perfectoid space, I get a genuine vector bundle over that ring. All right? And I could have made the same remark about pro-étale bundles one step back. It would just be modules over R itself. And let me maybe just remind you explicitly that 𝔹dR+, it's this sheaf of rings, which I'm not going to define, but let me just remind you what's the shape of it. So it's complete with respect to the topology defined by a certain principal ideal generated by a symbol T. And associated gradients for the T-adic filtration are just the structure sheaves on the pro-étale side twisted by I. But again, kind of as the results I'll say, and so there are many more basic pieces of evidence for that, the different pieces of filtration are glued together in an interesting way. And if you remember, if you looked at how this theorem is proven, the fact that the top two graded pieces in 𝔹dR+ are glued in an interesting way plays a crucial role in the appearance of differential forms here. But I'm going to remind you as we go on of why this is the case. Right, so this is not going to play a role, but let me just say it. So 𝔹dR+, so my notation is that 𝔹dR+, without the boldface font, this is just the value of that sheaf on C itself. So this is the usual Fontaine's ring. So by this, I would just mean representations of the pro-étale fundamental group into GLN 𝔹dR+. Okay. Yeah, because I wanted to have a lattice here for this to be fully faithful. But it's very interesting to understand the difference between these two categories and these two categories, but that I have nothing to say about. Okay. Yeah, right, exactly. So I think, right, all such, yeah, that is true, and all such statements reduce, well, these are all T-complete categories, so they all reduce to analogous statements mod T. Right? Yeah, maybe I should emphasize that here there is a functor of the mod T reduction. So you can have a local system E going to E mod T. Right? So in other words, this category of pro-étale vector bundles admits a natural and potentially interesting deformation linear over this ring 𝔹dR+. So, and moreover, we do get interesting objects there if we're originally interested in ZP local systems. So you might naturally wonder whether there's some linear algebraic description of this category. And that's what I want to talk about. Sorry, I just have these two boards, right? No board on the side. No, that would be okay. Yeah, I could replace it by ZP bar. 𝔹dR+ contains KP bar. Ah, right. Yes, I can't replace it with C. I don't think there is a. So, right. I don't think at least there is no natural functor from C local systems to 𝔹dR+ local systems. Right. Okay, great. So let me compactify the statement of this theorem a little bit. So I want to keep it on the board, so I'm keeping track of X2 tilde and the exponential map. So I'd like to, so I said that there was some interesting deformation of the category. So the question is, what does it correspond to? Well, if there was some more linear algebraic description of it. So, well, your candidate answer for it should better be a deformation of the right-hand side category to have a chance of getting a correct statement. So let me recall that there is a natural choice of such a deformation in the presence of this additional lift. So to make the kind of language a little easier, let me assume that I also have a lift all the way to bdR+. So let's say that X tilde is a smooth, well, I'm going to say formal, but I'm going to say in a second what I mean by this. Adic space over bdR+. So by definition, what I mean by this is just it's a collection of adic spaces I call X tilde n, so which are smooth over bdR+ mod t to the power n. So I just recall that this is, so it's some kind of topological algebra. Sorry, it's a Tate algebra where this is my ring of bounded functions. And I have this data for every n. And of course, with a formal scheme, the reduction of the n plus first one is the next one, is the previous one, sorry. All right. So I'm just reading it as a formal scheme. So there, I don't want to think of any kind of geometric object all the way over bdR+. All right. And my notation is that this is a lift of it's x1. And just for compactness, I'm going to denote this by x. All right. So I assume that suppose, so I was interested originally in this variety, so suppose I chose this lift all the way to bdR+. Oh yeah, thank you, sorry. Thank you, yeah, yes, great. Yeah. Yeah, sorry, your goal, yeah, bdR+ has a map to C given by the top quotient of this filtration, whereas, well, maybe bdR is not going to explicitly appear in anything of what I'm saying, so if it does appear, then I made a typo. All right, so what is my deformation of the category? Well, you could already guess where I'm going with this, so it should be a deformation of the category of Higgs bundles. So let me introduce what's called T differential operators. I'm going to call it dx tilde comma t. So this is going to be a sheaf of associative rings let's say for now just on the analytic side of X. So let me first give you an explicit but not the most helpful definition, and then I'm going to upgrade it to the right definition. So it's a special case, I think it's, if I understand correctly, it's the category due to Deligne, which is responsible for what Deligne was calling lambda connections, where now the value of lambda is this t. So it's the following algebra. So locally, it's generated by functions on my lift. Well, I'm going to emphasize that this is a non-commutative algebra, so I freely adjoin symbols like partial v with respect to every vector field. But also, so I'm going to implicitly, well, I'm just going to, everything will be t-adically complete at the end. Subject to the following conditions that I write down the usual conditions when I define differential operators, but now I've rescaled the commutation rule between vector fields and functions by t. And likewise, the commutation between two symbols corresponding to vector fields is also rescaled by t. So this is why this is not the great definition. So formally, yes, I do want to put a Tate twist there. Now, so this is an explicit definition. I'm going to say my actual definition in a second, where the Tate twist will appear immediately. Sorry, there's something messy. Oh, yeah, sorry, that wasn't very helpful. Yeah. Sorry, it's not the zero algebra, but it's not obvious from the definition anyway. Yeah, thank you. So commutator of the symbols corresponding to two vector fields v1 and v2 is the symbol corresponding to their usual Lie commutator times the element t. Okay. Right, so this is slightly unhelpful because it looks as if it depends on the choice of an element t. And also maybe it's, yeah. So I don't want to complete in any t direction. So far, it's just going to be algebraic differential operators. right? But I do want it t-adically complete, so it's always t-adically complete at the end. So maybe let me once write it explicitly. When they complete, they're not, but modulo every power of t, they are. So yeah, let me say what. Let me give you another definition, which will sort of make it a little clearer. Well, yeah, which will make it clearer that it only depends on the ideal generated by t, for instance. So this dx tilde t, it's also isomorphic to the Riesz construction of the usual t differential operators. So this is the union, again, after which I will have to p-adically complete, of the following. So I'm going to take t to the power I times the ith step of the order filtration on usual differential operators. So this is the ith step of the order filtration. Right, so I'm only including higher and higher degree differential operators if they come with a factor of t in front. So now it's clear that this only depends on the ideal generated by t, right? Sorry? No, sorry. So x tilde already has a t in it, right? This is over bdR+. So this is a subsheaf inside differential operators invert t. Sorry, this is, maybe I should emphasize, relative to bdR+. Okay. Thank you, yeah. Is that the question? Yeah. Okay. So now it's clear what I'm doing modulo t. So maybe it's even more clear from this definition is that if I kill t, then my condition is just this is a commutative algebra, right? Because I just declare all commutators to be 0. So this is the, please?
Can you use a microphone for the people on Zoom, please?
So the question was whether they would do the completion after the whole union procedure, and the answer is yes. So I don't want the completion to change the mod t reduction of what I'm doing. Okay?
Yeah, but it was so noisy. I'm sorry.
Oh, sorry, it was my voice. But oh, sorry, the question was, if I understood correctly, whether I'm doing the t completion after I take this union.
Yes.
And the answer was yes.
Yes.
Okay? Mm-hmm. So
It's much larger.
oh, each step is already t complete, right?
Yeah.
This is my setup. Yeah. Mm-hmm. So this was maybe Piotr's remark or somebody's that it involves infinite series of growing order with terms of differential operators of growing order, provided that there are higher and higher powers of t there. Okay. So I was saying that modulo t, I just get the symmetric algebra on the tangent bundle, and indeed, if I take this to be my official definition, I'm going to pick up a Tate twist here. Oh, sorry, there will be Tate twist by +1. All right, so if you recall, Higgs bundles are vector bundles on E with an action of this algebra, and I've now deformed this algebra, so I have obtained a deformation of the category of Higgs bundles, so let me introduce this. Let me write it down here. So yeah, so maybe to save space, let me state what we're proving. Oh no. So yeah, here is our theorem in progress. So that under the very same assumptions, so let me suppose that I have x tilde over bdR plus, this smooth, this time proper collection of data like this. So each of these guys is proper. So I'm thinking of it as a maybe additional, well, as a lift of my x living over c, and I also make a choice of this exponential. Which is a continuous map just as before. So the choices are exactly the same. Then there is a fully faithful functor. From vector bundles on x tilde M with an action of dx tilde t. So such that, well, as usual, when you define D modules, such that the functions sitting inside there act by the usual multiplication. So there's a fully faithful functor to bdR plus local systems. On X, where I recall my X is the special fiber of my deformation. So how does this fit with what I was saying before? So there is a mod T reduction functor going from here to just Higgs bundles. Correct. Yes, maybe I should emphasize it. Yeah. So yeah, I definitely don't want to consider bdR plus local systems on the analytic side. It'll be a very small category because this bdR plus on again on things which are 𝔹, which are connected 𝔹 over my x, it would just be the constant sheaf there. So this is Higgs bundles. Well, sure. It's so as a topological space, I want to treat x tilde as the same space as x. But yeah, it is equipped with an action of this whole sheaf. In particular, its functions on x tilde act there. That's a very good question. I mean, you could have likewise asked it there, right? It doesn't seem to appear in the state. Oh, okay, great. Yeah, so it's a very interesting story. I think when I talk about so. Let me say it in two ways. So it does. So I'll try to explain that this theorem is, in a sense, a formal consequence of that theorem. So all the real kind of work happens over there. So maybe I should defer that question to this theorem. But then I think when I'll talk about how this theorem gets proven and how this gets lifted to bdR plus, there'll be an appearance of an exponential map, and it's not immediately. The passage from it to this choice is not immediate, but maybe I should say this, and then you could ask this question again at the end if it's not satisfactory. Right, so. Correct, yes. So let me finish the diagram, and then, yeah. So this is Higgs bundles on X, and that, Ben proves for us, is the same as pro-étale vector bundles on X. So and the functor constructed so that this diagram commutes mod T. Sorry, the functor of reductions mod T makes it into a commutative diagram. So I strongly suspect that this functor isn't equivalence. We can, well, at least I don't quite see how to prove it at the moment, but it's definitely an issue. Well, it's an issue in my understanding. This functor should be an equivalence. So let me just make an orienting remark. That it's definitely an equivalence on rank 1 objects. But again, sorry, you shouldn't. I ask for your forgiveness and ask you not to focus too much on this non-fully faithfulness. That's I don't think it's an interesting aspect of the story. Correct. Yes. Well, I could invert T. Well, I mean, yeah, that I couldn't. That I sort of. Sorry, maybe what you're implying is actually still my passage from a ZP local system to a 𝔹dR+ local system was still a step which was losing information. So indeed, there are finer structures, which it would be wonderful to have a linear algebraic description on that. But I think that's what. Yeah, that's also correct. Yeah. Sorry, so I should just maybe I could have reduced here modulo every power of t. Yeah. Sorry, I'm not very well versed in this, so so indeed the construction of 𝔹dR+ a posteriori, yes, sorry, the construction of 𝔹dR+ is independent of that. Well, right. So maybe I could have said that I have a complete algebraic closed field over rank Van valuation. Right. Yeah, you're right. Yes. Sorry, I mentioned K just for orienting purposes, but now I'm going to make one remark where K appears. But yeah, indeed, nothing depends on K. So yeah, so the claim is that there is such a lift. So let me make some comments about this. Yes, right. Sorry, so this is a tensor functor, so it preserves ranks, so it doesn't use a functor on rank 1 objects. Sorry, so it's really a minor thing. If we had such a functor just defined not on vector bundles but on perfect complexes, it would have followed formally from the fact that it's an equivalence on mod t, that it's an equivalence here. But again, it's a weakness of character that we don't have this functor. So it's okay. Yeah. So yeah, let me make some comments. Yes, let me see what I was trying to say. Yeah, so let me make a remark, which I think might have been implicitly observed by somebody already, that it's kind of interesting because the right-hand side manifestly depends only on x, right? Whereas the left-hand side a priori depends on x tilde. So yeah, after the fact, you're proving that at least if you made the choice of this exponential, this category is this category for different x tildes are equivalent, which I don't know a direct proof of in this case.
Do you expect that statement to be true without the exponential?
It's a very good question. I don't see a reason, but yeah, it's good. Oh yeah, sorry. The Bargev's question was whether this category is independent of the whether this category only depends on x. Sorry, without the choice of an exponential. Thank you. And my answer was that I don't know. I don't quite see a reason. Yeah. So right then, kind of, why would you expect in general a relation between 𝔹dR+ local systems and TD modules? So there are a lot of kind of precursors to that, and somehow, which are very kind of helpful here. So first of all, so I stated this as a functor of abelian categories. But again, it should really extend to derived categories. But let me give you one statement which has long been known to be true on the level of derived categories. So I think it's a comparison theorem due to Scholze. And maybe in this generality is due to Heuer. But correct me if I'm wrong. So if I have any smooth x tilde over 𝔹dR+, so not necessarily proper anymore, then I could compare its pro-étale homology of its special fiber with coefficients in this period sheaf 𝔹dR+. You can calculate it in terms of the drum data, and it will be identified with cohomology of the Holling complex on x tilde. So it's almost the drum complex. Except that you rescale the ith term by the minus ith power of t. So you multiply the ith term by the sort of decreasing powers of t, so you make them larger and larger as you go on. In particular, now you've made it so that differential is 0 mod t, right? Because if you reduce it mod t, then tautologically the image of everything here is divisible by t. Sorry, the image of everything here is divisible by t, so your differential is 0 after you reduce mod t. So mod t, this recovers the comparison between pro-étale homology of the structure sheaf and double block homology. Right? But there's this lift. And how is it related to TD modules? So using a Cajou type resolution, you can show that this is the same as derived endomorphisms of the structure sheaf TD module. Right? This is a familiar statement for usual D modules, but the claim is that it's proven similarly for T. So my situation is that I have these two categories of TD modules and BdR+ local systems. And they're both tensor categories, and I have these and I have their respective unit objects, and I've identified endomorphisms of the unit objects. So maybe I should emphasize that this is an isomorphism of associative DG algebras at least. It's actually an infinity algebra, but at least here it's clear it's an associative algebra under composition, and this as well because BdR+ was a ring. So from this, it follows formally that there is an equivalence on some subcategories of these categories. So let me emphasize this. Therefore, as a consequence of this equivalence and of the fact that it's true for any smooth x, so it's true locally on x, I can identify the category of vector bundles on x tilde with an action of these differential operators. Such that if I reduce, so let me call this vector bundle M, such that the Higgs field on M mod T is nilpotent. So in other words, this is saying that locally on X, modulo T, I'm a successive extension of copies of the structure sheaf. And then this is equivalent to BdR+ local systems. On the pro-étale side of X. So let me introduce notation boldface E, such that on E mod T, which is now just a pro-étale vector bundle, what's called the canonical Higgs field is nilpotent. Correct, exactly, yes. So I haven't defined what canonical Higgs field is. Equivalently, this is saying that this vector bundle, it's a successive extension of pro-étale X modules, which come from genuine sheaves on the analytic side of X. But right, it has this, analogously to this. Here it was a successive extension of things with vanishing Higgs field. But I'm going to say something more about what this Higgs field is. It will be crucial for the constructions. So yeah, I think I misspoke earlier. I don't see a reason why it would be successive extension of locally free things. I think a priori it's only coherent, because your Higgs field, its rank might jump. Peter?
So in your theorem, fully faithfulness is proper. So how can you work locally?
Oh, sorry.
Repeat your question.
Peter's question was, there's a theorem, there's a theorem for the proper case, and now I'm having some discussion in the non-proper case. So the discussion I'm having right now, it's not a part of the proof of the theorem. It's just a remark that some stronger statements on these smaller categories have been long known. Okay? So, sorry, this is not a discussion of the proof yet. I'm going to make an analog of this statement, which is local on X tilde, but it's going to be slightly different. Does that answer your question? Sure, yeah. so Vadim's question is whether it's correct that neither of the categories depend on the exponential, but the functor depends on the exponential. Here, I think that's the case, just how it is the case already for the mod T reduction. But here, as Vadim remarked, this does not depend on any choices of the exponential. Okay? So nilpotent objects, it's okay. And maybe I should make a remark that there is a strengthening of this result, which I'm not going to state precisely, but so by 5 authors, so also extended to small subcategories by Liu, Ma, Ni, Chu, and Wang. So they choose some kind of integral model for everything in sight, and this lets them define some notion of smallness, which is an enlargement of the category of, which is a weaker condition than these nilpotence conditions. But let me not say exactly what this is. It's not going to be explicitly necessary for what I'll be doing. All right. Are there any questions so far? Oh, Daniel, yeah. No, I don't think so. Just how on the left, we very well know that they don't, right? Because, for instance, if you have a rank 1 bundle, what does it take to outfit it with a Higgs field? You just need to provide a 1 form. But it's only going to lift it to a T connection upstairs if this 1 form was closed. Right, so it's, right, so this is one of the, this is why somehow this doesn't formally imply fully faithfulness upstairs, if that's what you're getting at. Sorry, the question was whether this mod T reduction functor had a section. The answer was no. All right. So let me discuss what the idea of this construction is. And it's, right, so I'll try to argue that, I'll try to set up things in a way that this will be mostly a formal consequence of Faltings Heuer's correspondence modulo T. But this crucially relies on kind of a local version of this correspondence, which is this beautiful construction discovered by Bargov and Minja. So let me recall it. So it's what's called Simpson's gerbe. Yeah, so for a moment, we can forget about these BdR+ discussions, and this is just going to be a discussion of this equivalence, right? But I'm going to set up this equivalence in a way that's going to be helpful for me. So they observe the following. So if you have any smooth rigid-analytic variety, without any conditions, any lifts whatsoever, then they produce a natural gerbe, so GM gerbe. But again, it's only the analytic category, so maybe I should emphasize this. Gerbe, which I think they call Px, on the cotangent bundle of X. And again, there's a shift by 1 that I'm carrying around. So this is the, maybe, right, so this is the total space. Well, yeah. This is the total space of the twisted cotangent bundle, but again, it's isomorphic to the usual cotangent bundle. So there's this gerbe here which serves the following purpose. So it gives you an analog of this correspondence without any choices and for any smooth variety, not necessarily proper one, such that so they prove a more general derived statement. But let me just for concreteness state the abelian statement, such that the pro-étale vector bundles on X are equivalent to coherent sheaves on T star X, which are twisted by P, which are locally free over X. And I'm going to say what I mean by this, that are so what do I mean by this? Well, it's a non-trivial gerbe, so I have some sheaves twisted by this gerbe. So there is not really a push-forward functor down to X. But this gerbe is Right, so it's trivial 𝔹 locally on X, and so this is locally freeness condition that I can check after this trivialization. So maybe I should emphasize, maybe I should make this remark that I should have made earlier, but which is really bookkeeping. So coherent sheaves on T star X, which are without any twist, which are locally free over X, are the same as Higgs bundles on X. Via the push forward functor. So if you have a coherent sheaf on T star on X, so you can push it forward to get a, well, a priori some sheaf on X, but if it was, well, under this condition, it would be locally free on X. And the fact that it came from a cotangent bundle would correspond to the action of the Higgs field. So this was the geometric interpretation of Higgs bundles. But now they claim, they discover that there is some gerbe such that if you consider sheaves twisted by this gerbe, then this is always identified as pro-étale vector bundles. Right? So I'm not going to define this px for you, but let me put myself in a situation where I do have a lift, and then I'll define px for you explicitly. Because I'm going to define a certain finer object whose existence will be crucial for me. Yeah. Mm-hmm. Are there any questions about this setup yet? I haven't defined this px still. This px. So the question was whether we can lift this gerbe to BdR+. I think it's a very good question, and it's probably the question which I'm trying to answer. But to me, it wasn't immediately obvious what does it mean. So where is there a scheme where we're trying to lift it to? Right. That's one guess. I think that's so I think that's not quite what you want to do, because you see the category you're trying to identify here, these BdR+ local systems. Contrary to pro-étale vector bundles, this no longer has a large center. So it's not that I'm really not expecting it to relate it to Higgs sheaves on X tilde. For example, for many reasons, as I can compute already on this nilpotent level. But yeah, so this is but we are going in a way to form this gerbe, and this was the main observation. But yeah, which Vadim pointed out, and it was beautiful. So I'm going to explain it right now. Okay. But first, let's discuss what we're deforming. Sorry, Ziyu, does this answer your question? Okay, great. So what are we going to be deforming? So I have this GM gerbe, but in the presence of a lift. So if x tilde 2 is a lift of x, there is a natural mu p infinity reduction, which I'm going to call p x tilde 2 of px. So I have the group, the sheaf of groups mu p infinity on the 𝔹 side. It embeds into the sheaf of groups GM. And so I claim I had a gerbe for this larger group scheme, but then there is a canonical reduction to this subgroup scheme, right? So here, maybe it didn't matter for GM, but here when I say gerbe, I always mean gerbe for the 𝔹 topology, right? So it's represented by some, its isomorphism class is encoded by some second 𝔹 homology class with coefficients in this infinite group. So let me just tell you what this px tilde 2 is. Because in particular, this will, at least the exponential will appear. So how am I going to use x tilde 2 to define it? So, and if I tell you that, of course, the a posteriori, you'll learn what px is, at least in this liftable case. So let me write down, so it has a class in second 𝔹 homology of x with coefficients of T star x with coefficients in mu p infinity. And let me tell you what this class is. So let me write down its Ionetta representative. So let me recall two pieces of data, which will be important for me. So first of all, how am I going to use the lift? So if I have a lift x2 tilde, then there's something called Faltings' extension. So it's a pro-étale vector bundle on X, which is naturally constructed out of this lift, which is an extension of omega 1 x. Again, I'm carrying around the state twist by OX. So these are two vector bundles on classical vector bundles on X, which I view as pro-étale vector bundles. And I claim that there is a natural extension between them, which now is for any positive dimensional X, it's genuinely pro-étale. It does not descend to a vector bundle in the analytic topology. So let me tell you what it is. So implicitly, if you believe this bottom theorem that Faltings and Ben prove, well, already, yeah, for that, so you only maybe need Faltings as generality, then this fx tilde 2 is the, so if I'm going to denote to this functor by h, is h for Higgs of the following Higgs bundle. So it's just the direct sum of vector bundles OX and omega 1x equipped with an nilpotent Higgs field, which is right, which is given by this map. Right, so if I take this direct sum of vector bundles, there is a natural map from the second summand to the first summand tensor omega 1, just because it's an omega 1. So on any smooth variety, there is this natural two-step nilpotent Higgs bundle. So if I'm going to believe this correspondence, there should better be a corresponding pro-étale vector bundle, and that's what it is. But also, right, but it will be important for me, if I don't run out of time, how this fx tilde 2 was actually constructed. And let me emphasize this. So yeah, very good point. So Ellen's point was that to talk about this h, I need to choose an exponential. In general, yes, but here this is a nilpotent Higgs bundle for which I only need to, I don't need the choice of an exponential, I only need a lift. This was a special case of this discussion which we had here. Well, I could have dropped vector bundles here, right? Yeah, that's a very good point. So yeah, let me say what this fx tilde 2 is doing. So let me get rid of that. So, okay, maybe it's not, well, I'd argue it's a definition, but maybe formally it's a characterizing property. So if R is any perfectoid space, affinoid perfectoid space mapping to your X, then there is a natural equivalence between splittings of fx tilde 2 evaluated on R. So I told you that when I evaluate any pro-étale vector bundle on a perfectoid, I do get a projective module of the correct rank. So there I get this extension, which of course is somehow split, but there are many different splittings. And so there, splittings of this are in a natural bijection with maps from the pullback of the structure sheaf on this x tilde 2. So I just think of it as a sheaf on a topology. So my x is outfitted with this nilpotent thickening of the structure sheaf. So I pull it back here. And there should be a map to the analogous thickening for R, right? So the whole kind of feature of this business is that every structure sheaf on this pro-étale site comes equipped with a natural thickening whose value on perfectoids is just this 𝔑dR plus mod t squared. And I could compare it with thickening of x tilde 2. So it's in bijection with ring with 𝔑dR plus algebra maps. Such that S is equal to identity mod 2, or to the canonical map mod t. Okay? So the existence of this splitting is kind of equivalent to the fact that on the pro-étale site, I have every object has a canonical thickening of a structure sheaf. All right, and now I need to define for you this x2 class. So for that, let me introduce a final piece of notation. So I'm going to define a subgroup of this group for which I originally had the gerbe. So it's going to be the subgroup. It's going to be an open disk around 1. So it's the set of elements such that the distance to 1 is strictly less than 1. And the significance of this, so its C points is this 1 plus MC that appeared before. That's exactly where the logarithm is defined. So now I can write down a short exact sequence on X pro-étale. It's going to be obtained by gluing Faltings' extension. So it's an extension of omega 1 x minus 1. So I'm going to glue it to another extension, and that extension is going to be this group U. So it admits a logarithm map, back to the structure sheaf, which is just a map of sheaves, but it's represented by a map between actual rigid varieties from this open disk to the affine line. Maybe I should emphasize this. And well, now I compose this, but this was an injection. And so the kernel of this map is the same as the kernel of this logarithm, which is exactly mu p infinity. Right, so I wrote down for you a gluing of two x1 classes, which is this x2 class. So it's an extension of omega 1 by mu p infinity. And now this formally, well, it's actually even more structure, but this formally gives me a class in second pro-étale cohomology of T star x with coefficients in mu p infinity. Because now, for instance, whenever I have a test scheme mapping to the cotangent bundle, I could pull it back there to get the gerbe there. But now finally, I'm going to note that a priori, you see here I used some kind of non-classical pro-étale object, but ultimately I'm getting a cohomology class with coefficients in an étale sheaf. So it was pulled back from the étale side. So this is the same as the étale cohomology, but still crucially taken in a rigid-analytic sense. So I do get an object of classical rigid geometry. Okay? Even though I no longer, perhaps I no longer have an explicit Yoneda presentation for it, right? Okay. So I do get this natural class, and this beautiful theorem that they prove is that if you consider the induced GM gerbe, then twisted sheaves for it are pro-étale vector bundles. Right? So how am I doing on time? Yeah. So let me now maybe address Zayu's question: is how are we going to lift this over 𝔑dR+? So. Let me define the category of twisted, so category of d x tilde t modules twisted by this gerbe. B x to tilde, which I'm going to note by p. And yeah, I think the fact that such a construction should exist was pointed out by Bargev. And then, how do you execute this? So you have, well, we know very well what does it mean to twist the category of Higgs bundles, of Higgs sheaves by this gerbe, because it's just a gerbe on the cotangent bundle. Now I have some deformation of this category. And the observation is that because this was an étale group scheme, the gerbe I can formally extend this to a twisting of this deformed category. And so this rests on the following lemma, which I'm just going to state in abstract algebra without topology for concreteness. So suppose you have any associative ring. And it has a two-sided ideal. Which is nilpotent. So for some n product of any n tuple of elements is 0 in any order. And so such that A mod I is actually commutative. Oh, I apologize. I should have called this tildes. And this is going to be my A. To be consistent. All right. Then there is an equivalence between étale ring maps from the reduction to R. Okay, so here, well, R is commutative. That's the only setting in which I know what étale means, and A is commutative. And ring maps, so flat ring maps from A tilde to R tilde, such that the reduction is étale. So in other words, I'm saying that every 𝔹 algebra admits a canonical flat deformation over this non-commutative deformation of A.
Use the microphone.
Oh, sorry. So maybe you're saying I should demand that this is commutative for it. Does that help? I think they're not working, we were told. But I want to understand what the question was. Yeah. So. Uh-huh. Oh, sorry.
Something where you both different connected components in I mod I square, you could have something where somehow different connected components of A mod I are intertwined, and then you would, I think you would not, but maybe you can.
Sorry, I thought it was okay. Let me state a theorem. Let me state what we're actually proving. I thought that the brief goes through immediately for that. So let me make the following assumption. So this ideal is generated by a central element. Okay? Sorry, I thought it would be important for some applications. Sorry, no, you're completely right. I thought it was okay, but.
You didn't repeat the question.
Oh. Well, there's no question anymore. But. Sorry, offer very, very hopefully made a correction that he thinks that my original statement was false. I thought it was okay, but he's probably right. But now I think we both agree that it's correct. Is that okay? Right. Well, thank you very much. So how am I doing on time? Okay. So I'm out of time, so let me just say that now, verbally, how am I going to apply? So this lemma is very familiar for commutative rings. I claim that it goes through for associative rings if your reduction is commutative. But now how am I going to apply this? Well, I claim that now I have some 𝔹 cover of my cotangent bundle which trivializes the gerbe. And now I'm going to lift it to some strange D module, but which kind of is an object. So application will be that A will be functions on the cotangent bundle, and A tilde will be these T differential operators. So I'm going to lift this 𝔹 cover which splits the gerbe. Now also on the iterated product of this cover, I'm going to have a torsor which is the gluing data for my gerbe. But it's also all 𝔹 because this is an 𝔹 group scheme. So I'm going to be able to lift all of that there. And I'm going to be able to define the notion of a twisted D module. And what we're proving is that there is a function from those twisted D modules to these bdR+ local systems. Right, which somehow, well, I unfortunately didn't get to it, but it relies on the exact shape of this explicit X2 extension. So I apologize for going out of time. Let me stop here.